Hello, Laurier Shads. Welcome to our final week. So by now, we've all had our bridges for quite a while, and those of us that had time put them together, and we've all had a chance to look at them and look at the different designs and figure out which one should be the strongest one and make our best guess at how much force it's going to take to break one of these things. So we're going to have some fun. Before we can have that fun, we have to figure out how we're going to go about breaking these. So we've got a couple of stands that we built in the lab for exactly this purpose a few years ago, and we've modified them a little bit, and we put a 3-to-1 block and tackle. The scale that we're using only goes up to 50 kilograms, and we just want to hedge our bets that we're going to be able to break this thing before we run out of range on that scale. In this CAD drawing, you can see that the stands are on 2x2s, which transfer the load to the bottom of the stand. And we've got a heavy cable that goes up around a pulley, back down under the other pulley, and then it attaches to our digital fish scale. From there, there's another cable that goes to a cranking device so that we can put some load into this thing, and then it goes up and it attaches to the dowel in the bridge. So with this 3-to-1 reduction, what it means is that whatever we see on the scale, 3 times that force is actually going to be felt by the bridge. So let's get dressed up in our fanciest clothes, and we'll get one of these set up. And we'll start breaking bridges. To create our force, we're just going to use a ratcheting tie-down strap. This one is rated for a maximum force of 227 kilograms. So hopefully it'll do the trick. So we'll make sure that our weight scale is visible in the other camera, and we'll start cranking this bridge down. And so we're putting the load right on the dowel at 3 times whatever our scale is reading. And you can see I'm beginning to crank it pretty hard there. And the back right corner seems to have collapsed. Let's go have a look at that. So when we look at this, what we find is that the bridge itself didn't break. The little cross pieces that are intended to locate the load at each end of the bridge, they broke. You can see the little triangles broken off here. And what happens is the whole load winds up pressing up on that plate, which is not designed to take an upward load at all. So what we're really looking at here is a design failure. So we'll glue this back together, and we'll go back to the drawing board a little bit on how we transfer the load into the bridge. With that all said, 38.33 kilograms times 3 was a pretty good load for a 177-gram bridge. And we're back. We've glued this bridge back together, and you can see at the end there we've added a dowel that goes all the way across. So that makes sure that the load is carried from one side to the other, and it goes into the upright sides of the bridge. And the dowels are held in place with a piece of tape against the little rails so that they're both in the exact same position. We'll just get things stabilized here, and then we'll start cranking. You can see we're cranking in slow motion. And there's our reading. Doesn't seem to be working though, the reading. But the bridge did break, and pretty spectacularly. So let's look at that again in slow motion. So it's pretty cool because the one side kind of starts to fold in, and then it just lets go. And it actually explosively blows out the side of the bridge, and then it's all over. It just falls apart from there. But not to worry. We have a laser cutter, we had some more wood, so we made another bridge, and then we took it to the lab and we broke it there, and this time around, we got data. Well, that was pretty spectacular. And wow, 142 kilograms. That is one strong bridge. Let's have a look at that again in slow motion, because it was pretty hard to see what was going on. Afterwards, we took our broken pieces, took a picture of them, and put them on the weight scale. You can see that we didn't lose any mass, so no fission occurred. Okay, so moving on. Let's set up the truss bridge, and we'll try this again and see how the truss bridge does. In this case, when we start cranking down, the back of the bridge, one of the uprights will kind of fold in, and then the bridge doesn't totally explode the way it did with the slab side. It just becomes kind of bendy and won't really hold a load. So in this case, unlike the first bridge, it didn't hold, and then all of a sudden explode. It's not as stiff, it's much more bendy, but it also didn't hold nearly as much peak load. So it's not as strong a type of bridge, at least not with this particular construction. When we look at the actual damage, it's pretty cool. You can see that the top actually kind of went side to side rather than just being pulled straight down. And then when it broke, the floor let go as well. But the other side still held because it was able to flex to distribute the forces. To make sure that it didn't break at such a low value due to some sort of internal flaw, we did it again in the lab. Ultimately, this bridge broke in about the exact same spot and about the exact same way, and at pretty close to the exact same amount of force. Once again, we didn't turn matter into energy. Well, we're down to our last bridge. This is the arch-type bridge. It's going to be a little bit lighter than the other ones because somebody forgot to cut the one cross piece. So we've got it in our apparatus here, and we're going to crank it down while we record the amount of force that we're putting in. Well, that was kind of fun. Like the truss bridge, it only broke one side and the rest of it flexed. But also, like the slab bridge, it actually blew a piece halfway across my driveway. Let's have a better look at the damage. So it looks like the cross member at the very top was actually the first thing to go. That's the part that blew across the driveway. That took out the arch at the top, which in turn took out one of the uprights, which in turn took out the floor on that side. At 128.37 kilograms, this wasn't quite our strongest bridge, but it leaves for some good discussion for the Shads. Which bridge would be the strongest had I not forgotten to put that extra cross piece in it? And what would it take to strengthen the existing designs? What small change could we make to greatly increase their strengths? So that's for you to discuss in your groups, and let me know what you think. I hope you enjoyed this. Thank you.